I'll take up carbohydrates. Okay. So introducing you to the core features of Oracle. Here at Oracle, we have live classes to elevate your learning experience. Then we also provide you with recorded lectures so that you're able to access them anytime as per your convenience. Then we also give you notes which are based on the latest CBME syllabus, and then also provide you with MCQs so that you're able to assess your standard of knowledge gained. Okay. Then a very unique feature of Oracle is that we have personalized counseling sessions here. So apart from the academic support that we're already providing, if you need any non-academic support, then also you can book a slot with us anytime. Then here at Oracle, we have three different subscription plans. That is basic, which is for 3 months and comes at 15,000, followed by the standard plan, which is for 6 months and comes at 30,000, and the mentorship plan, which is for 12 months and comes at 50,000. So in the mentorship plan, you'll also be having live doubt clarification sessions, personalized guidance, and you'll also be provided with notes. Then you can get an additional 20% off by using my promo code as displayed here on the screen. Okay. So this series is based on rapid revision of all the important topics. All the high yield questions will be covered. All the volatile quick facts will be taken up. So in this class, I'm going to take all the important cycles here that are included in carbohydrate metabolism, your glycolysis, glycogenolysis, TC and HNP. These 6 cycles are like really important. Okay, very important. I'm going to mark them important. And then these Rappaport and lubricant cycle, these two, you often get them in short notes. Okay, short notes. These are for long question and answers. Okay. And then this fructose, galactose, and lactose metabolism, as such, nothing from metabolism is ever asked, but the clinical, you might sometimes get asked, for example, your fructose intolerance. From here, this is the most frequently asked question. Okay, so I'll try to cover the entire unit if it's possible. Otherwise, at least I'll try to cover these 6 cycles. Okay, the major 6 cycles. So there's equal probability of any of these cycles being asked. So you should do them. Be sure that at least one of them will be asked. Okay. And the cycles will be covered under these headings. That is the pathway or the cycle itself, the steps, followed by the site and the organelle in which it is taking place, whether the cycle is taking in the fed state or the fasting state. The energetics is important. Okay, then regulation is also important for any cycle. Then the clinical, of course, this is very important because we are studying all this for the sole purpose of studying the clinical, the diseases associated with. And then under miscellaneous, if there's something extra for that cycle or pathway that you need to know, I'll take that under the heading of miscellaneous. Okay, so beginning with glycolysis, very important. So what is happening after you've had your meal? The blood glucose level is high. That is when your glycolysis is going to take place. So your glucose is going to enter the cell. It is acted upon by hexokinase. Hexokinase is going to phosphorylate the glucose. That is, it is going to add a phosphate to it. So for that, where is that phosphate coming from? It is coming from ATP. So one phosphate from ATP is given to glucose and forms glucose 6-phosphate. Okay. Now this glucose 6-phosphate, this is the first step. And here this significance of this step is that it is involved in trapping of glucose, so that the glucose that is entering the cell, it does not leave the cell. Okay, because your glucose transporters, they are bidirectional. So the glucose is trapped in the cell for various metabolic fates. Okay, because glucose 6-phosphate does not only have one fate of entering glycolysis, it has various other fates as well. That is, it can go for glycogen synthesis, Then it can also enter HMP, then it can also enter glycolysis. That is one fate, but it also has other fates like glycogen synthesis, HMP, uric acid pathway. Okay, then what happens? Your glucose 6 phosphate, it is going to isomerize. So the enzyme is phosphohexose isomerase. Then it forms fructose 6 phosphate. Now this fructose 6 phosphate, to this another phosphate is added. You can see it becomes fructose 1,6 bisphosphate. The enzyme is phosphofructokinase here. This is a rate limiting enzyme. It forms the bottleneck of the reaction. This is the committed step. Okay. So this is the committed step. It forms the bottleneck of the reaction. Okay. And you can see where is the phosphate coming from? Another ATP is being utilized. So one ATP was utilized in the first step here. Now another ATP is being utilized here in this step. It forms what? Fructose 1,6 bisphosphate. Okay. If you try to understand these reactions, you will not have to mug up. Okay. Glucose is entering. You have to trap the glucose. So you add a phosphate. Now this glucose 6 phosphate is isomerizing. So it is going to change into fructose 6 phosphate. Now this fructose 6 phosphate, another phosphate is being added. So it becomes a fructose 1,6 bisphosphate. Now what is happening? Splitting is taking place. Now splitting up reaction is taking place. And what happens? This is brought about by the enzyme aldolase, and your fructose 1,6 bisphosphate is split into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Okay. Since the next enzyme in this pathway, that is glyceraldehyde 3-phosphate dehydrogenase, it can only act on glyceraldehyde 3-phosphate. So your dihydroxyacetone phosphate is also changed into glyceraldehyde 3-phosphate. Now what happens from here onwards? All the enzymes or all these steps, they are going to be doubled, okay, because you have two molecules of glyceraldehyde 3-phosphate. Now what happens? Your glyceraldehyde 3-phosphate, it is acted upon by glyceraldehyde 3-phosphate dehydrogenase and it forms 1,3-bisphosphoglycerate. Okay, so this is a dehydrogenase enzyme. You can see one NAD is being used and it is changed into NADH. Okay, and inorganic phosphate is being incorporated to form 1,3-bisphosphoglycerate. Okay, so there's phosphate at position 1 and phosphate at position 3. Now what happens? 1,3-bisphosphoglycerate is going to act and one ATP molecule you can see is being formed. So this is substrate level phosphorylation. Substrate level phosphorylation. That is the substrate in this case, which is 1,3-bisphosphoglycerate is giving a phosphate to ADP to form ATP. Okay, and the product that is formed here is 3-phosphoglycerate. Now this 3-phosphoglycerate is acted upon by a mutase enzyme. So this is an isomerization reaction. What is taking place? There is transfer of phosphate taking place, but it is taking place within the same molecule. So from the position 3, the phosphate is moving to position 2. So this is an isomerization reaction and this is brought about by phosphoglyceromutase. And what is formed? 2-phosphoglycerate is being formed. Now this 2-phosphoglycerate is acted upon by an enzyme known as enolase. And this enolase requires magnesium. Okay, and what is formed? Phosphoenol pyruvate is formed. Now, this phosphoenol pyruvate is acted upon by pyruvate kinase. Again, this is a substrate level phosphorylation. One ATP molecule is formed, and ultimately, you're getting what? You're getting pyruvate. Now, this pyruvate, it has two fates. Okay, so basically, if I give you an overview of glycolysis, what is happening in glycolysis basically is you have glucose, okay, which is a 6-carbon compound. And now this glucose, it is split into two 3-carbon compounds. One is your dihydroxyacetone phosphate and other is glyceraldehyde 3-phosphate. And I said that the next enzyme after the splitting reaction, after the action of aldolase, it can only act on glyceraldehyde 3-phosphate. So your dihydroxyacetone phosphate is also changing into glyceraldehyde 3-phosphate. Now this glyceraldehyde 3-phosphate ultimately forms what? It forms pyruvate. So this is basically what is happening in your glycolysis. Okay, and now this pyruvate that is formed, this pyruvate, it can have two fates depending upon the presence or absence of oxygen. So if your oxygen is present, then this is known as aerobic glycolysis. And what is formed? Acetyl CoA is formed. And in case oxygen is absent, then this is known as anaerobic glycolysis. And what is formed? Lactate is formed. Okay, as you can see here. So what is happening in case of anaerobic glycolysis? Your pyruvate, it is going to change into lactate, and the enzyme is lactate dehydrogenase. And in this reaction, what is happening? Your N is being formed. So basically, what is happening? Your NAD is being regenerated, and this step is of importance in this significance of anaerobic glycolysis can be seen in RBCs. Okay, so in RBCs where there is no mitochondria, because your RBCs there is no mitochondria. Okay, so no electron transport chain. So no electron transport chain, no mitochondria. What is? There will be no regeneration of NAD plus taking place. So in your RBCs, this step becomes your anaerobic glycolysis. It becomes very significant. Okay, so anaerobic glycolysis is significant in RBCs because your RBCs, they do not have any mitochondria, so no electron transport chain will be taking place. So how will your NAD will be regenerated? Okay, so this is the reaction through which your NAD is going to be regenerated. And where do you need this NAD? You can see here in this reaction, NAD is needed. This reaction here, NAD is needed. So the source of this NAD regeneration in RBCs is through anaerobic glycolysis. Okay. Now your glycolysis, it takes place in all the organs, and the organelle is cytoplasm, and it takes place in the well-fed state. Obviously, that is when you want to regulate or bring down your blood glucose level. So insulin in that case is released and your glycolysis is going to take place. Now talking about the energetics of aerobic glycolysis first. So in your aerobic glycolysis, as you can see, 4 ATPs have been generated. 1 ATP here and 1 ATP here. And sorry, not here. 1 ATP here and 1 ATP here in this step. Okay. So 2 ATPs in these steps are generated, and each of them is giving 2 ATPs because this glyceraldehyde 3-phosphate, there are two molecules of glyceraldehyde 3-phosphate. Okay. So from 1,3-bisphosphoglycerate, we're getting 1 ATP, and there are two molecules. So you will get 2 ATPs. And from phosphoenol pyruvate to pyruvate, you're getting 1 ATP. And since there are two molecules, so everything is going to be multiplied here onwards 2 times. So you get 4 ATPs from substrate level phosphorylation. Okay, so 4 ATPs are being generated, and how many NADPH you're getting? 2 NADPH you're getting because there's one step which is giving 1 NADPH. Okay, and since there are two molecules, so you get 2 NADPH. Okay, so 1 NADPH in the electron transport chain gives 2.5 ATP. So 2 NADPH will give 2 into 2.5, which is 5 ATP. Okay, so you are getting a total of 9 ATPs, but 2 ATPs are consumed in the initial stages, that is in the hexokinase and the phosphofructokinase. Okay, so 2 ATPs consumed, so you get a net ATP of 7 ATPs generated. That is the energetics for your aerobic glycolysis. Now talking about anaerobic glycolysis. In anaerobic glycolysis, what is happening? There is no involvement of electron transport chain. Your NADPH is being used by lactate dehydrogenase, so you do not get those 5 ATPs. So 4 ATPs generated by substrate level phosphorylation, 2 ATPs consumed in the initial steps. So you get a total of net ATPs generated as 2. Okay. Now talking about the regulation and inhibition. So the regulatory enzymes operate under the influence of insulin. Okay, sir, what are the regulatory enzymes in glycolysis? Your hexokinase, phosphofructokinase, and pyruvate kinase. These are the key regulatory enzymes and they are operative under the influence of insulin, and insulin is going to dephosphorylate these enzymes. Dephosphorylate. So they're going to be active in dephosphorylated state. Then apart from that, if we talk about the allosteric regulation, so your glucokinase is activated by insulin, your pyruvate kinase is activated by insulin and fructose 1,6 bisphosphate, and phosphofructokinase is activated by insulin, AMP, fructose 6 phosphate, and fructose 2,6 bisphosphate. And the allosteric inhibitors of these enzymes are for hexokinase, it is glucose 6 phosphate. For glucokinase, it is glucagon. And for pyruvate kinase, it is glucagon, ATP, and cyclic AMP. And for phosphofructose kinase, it is glucagon, ATP, citrate, and low pH and cyclic AMP. So basically, the products are going to be the inhibitors, and the substrates are going to be the activators. Okay, like you can see, ATP is generated from glycolysis. So ATP is the inhibitor, and your low energy level, that is AMP level, it is going to be the activator. Okay, so that's a general rule. Now moving on to the next cycle. So we've covered glycolysis, very important. Now we're going to talk about gluconeogenesis, another very important cycle. So talking about gluconeogenesis, you cannot say that it is the exact reversal of glycolysis, because your glycolysis have irreversible steps. Okay, so those steps, they cannot be reversed. Rather, they are what? They are circumvented. They are bypassed. Okay, so you cannot say that it is the exact reversal of glycolysis. So this was your glycolysis taking place. Now what is happening here in this case? See, from here, your pyruvate is going to form, first it is going to form oxaloacetate, okay, and then this oxaloacetate is going to form phosphoenol pyruvate, okay. So your pyruvate will not be directly forming phosphoenol pyruvate, okay. There is no enzyme to reverse this step, rather it is circumvented, that is this step is bypassed, okay, because this was one of the irreversible steps of glycolysis, okay. Rest, the reversible steps of glycolysis, they will be common to both gluconeogenesis and glycolysis, and the irreversible steps, they are going to be circumvented, okay. So in gluconeogenesis, basically what are we trying to do? We are trying to synthesize glucose from non-carbohydrate sources, okay. So synthesize glucose from non-carbohydrate sources. Okay, that is from new sources, new substrate. Okay, now what is happening? When was your glycolysis taking place? If we talk about the concept of glycolysis and gluconeogenesis, so glycolysis was taking place in the well-fed state to decrease your glucose and generate ATP. Okay, so glycolysis, it takes place in well-fed state. Please pay attention to the concepts that I'm giving you here, because they are basically the integration of metabolism. Okay, so you should know at what stage which cycle is taking place. Okay, just learning up the pathways, that might fetch you marks, but at the end of the day, you'll be really curious, okay, that when at what stage or when is which cycle taking place. Okay, so after you've had your meal, so that is the well-fed state. The initial 1 to 4 hours after you've had your meal, the blood glucose level increases. That is known as the well-fed state. Your blood glucose has increased. Now the body will try to decrease the blood glucose. That is when your glycolysis is going to take place. So glycolysis will decrease the blood glucose level and it is going to generate ATP. That is why you're having meals, okay, to get ATP, to get energy. Now, what happens? Early fasting state, that is after 4 hours. That is early fasting. Within the 4 hours, that was the well-fed state. Now, early fasting, that is from 4 to 16 hours after you've had your meal. What is going to take place? Glycogenolysis is going to take place, okay? Glycogenolysis is going to take place. That is whatever glycogen, stored glycogen is there in the body, that is going to be broken down to provide you energy, okay? And after 16 hours, what's going to happen? The glycogen reserves in the body have been depleted. So glycogen is depleted. Now the glycogen reserves have, because you have a limited reserve of glycogen, what happens? So after 16 hours, from 4 to 16 hours, body is trying to get glucose from the glycogen. Now what happens after 16 hours, the glycogen is depleted. Now that is when the body enters the fasting state, okay? So that is around from 16 to 18 hours. That is now the body is entering the fasting state, and this is where your gluconeogenesis takes place. Okay, so the body is now trying to synthesize its own glucose. Now, this gluconeogenesis, the synthesizing of glucose, this requires ATP. Okay, so gluconeogenesis, this requires ATP, and this ATP here is provided by beta oxidation. So the role of beta oxidation in early fasting, it is not to provide ATP, to provide fuel, but rather it is to support your gluconeogenesis. Okay, so this is, the beta oxidation is going to provide ATP, and also the beta oxidation is going to provide acetyl CoA. Now, this acetyl CoA, it is an allosteric activator of a key enzyme in gluconeogenesis. That is, yeah, I think we lost connection. Yeah. So here I was talking that in the fasting state, the role of beta oxidation is to support gluconeogenesis. Okay, it is going to provide acetyl CoA, and acetyl CoA is an allosteric activator of an important key enzyme in gluconeogenesis, and that is pyruvate carboxylase. Okay, so now let's see the steps that are circumvented in gluconeogenesis. So the first step is going to be that of pyruvate kinase. How is it circumvented? The pyruvate is first going to form oxaloacetate, and then that oxaloacetate is going to form phosphoenol pyruvate. So that is how this step is circumvented. Then all the steps are common to gluconeogenesis and glycolysis until you reach which step? You reach here, that is fructose 1,6 bisphosphate. So fructose 1,6 bisphosphate to fructose 6 phosphate, which was in glycolysis. This step was taking place by phosphofructokinase. Here, this is circumvented by fructose 1,6 bisphosphatase, and then you form glucose 6 phosphate. Now, glucose 6 phosphate to glucose is going to be formed by glucose 6 phosphatase, and glucose to glucose 6 phosphate in your glycolysis, this was taking place by hexokinase. Okay, so we can see here your pyruvate forms oxaloacetate. What is happening? Pyruvate is a 3-carbon compound, And your oxaloacetate is a 4-carbon compound. So what is happening? Carboxylation reaction. So this is a biotin dependent carboxylation reaction. Biotin dependent carboxylation reaction. You can see here carbon dioxide molecule is being added. This is an ABC reaction. ATP is needed, biotin is needed, and carbon dioxide is needed. Okay, and you get oxaloacetate. Now, this oxaloacetate, it is going to, this pyruvate was in the mitochondria. Okay, so through the malate oxaloacetate uh, and aspartate shuttle, malate aspartate shuttle, this oxaloacetate is going to come out into the cytoplasm. Okay, now this pyruvate was in the mitochondria. So therefore, we say your gluconeogenesis is partly mitochondrial and partly cytoplasmic because this reaction is taking place in the mitochondria. Now, this oxaloacetate is going to come out into the cytoplasm through the malate aspartate shuttle. Malate aspartate shuttle. Okay, now what is going to happen? Your oxaloacetate is going to change into phosphoenol pyruvate, and one GTP is required. The enzyme is phosphoenol pyruvate carboxykinase, and carbon dioxide molecule is liberated. Now, rest of the reactions, they're all the same. Common to glycolysis and gluconeogenesis. Then what happens? Until you reach fructose 1,6 bisphosphate. Now, one phosphate group is removed. The enzyme uses fructose 1,6 bisphosphatase and you get fructose 6-phosphate. Then this fructose 6-phosphate isomerizes to glucose 6-phosphate. Now, from this glucose 6-phosphate, phosphate is removed. The enzyme is glucose 6-phosphatase and you get glucose. So, this is how glucose is being formed in gluconeogenesis. So, the site, it takes place only in liver and kidney organelles, both cytoplasmic and mitochondria. I've just explained you how. Fasting state. So this cycle is taking place in the fasting state. I've just told you in the which fasting state here from 16 to 18 hours. That is after 16 hours. So that is when it is going to take place. And energetic 6 ATPs are relation. So there is covalent modification. Your glucagon activates regulatory enzymes by phosphorylating them. So your glucagon is going to activate the regulatory enzymes, that is your pyruvate carboxylase, phosphoenol pyruvate carboxykinase, your fructose 1,6 bisphosphatase and glucose 6-phosphatase. They are all going to be activated under the effect of glucagon when they are phosphorylated. Then talking about the allosteric activation, acetyl-CoA activates pyruvate carboxylase, and acetyl-CoA is always an activator of gluconeogenesis but never a substrate for gluconeogenesis. Remember this point, this was asked once in MCQs in NEET PG. Now talking about the reciprocal regulation of glycolysis and gluconeogenesis. So in glycolysis and gluconeogenesis, they are the reciprocal pathways. Okay, one is generating glucose and the other one is utilizing glucose. Okay, so they should be very well regulated, that when one of the pathways is active, the other should not be active or the other should be inactive in order to avoid futile pathway. So this is brought about by the use of a bifunctional enzyme, that is phosphofructase kinase 2. Now, what is a bifunctional enzyme? That is single polypeptide chain is going to have two enzymatic activities. So this phosphofructokinase, it has a kinase activity here and it also has a bisphosphatase activity. So bisphosphatase, it is going to remove phosphate, and kinase, it is going to add phosphate. So what is happening in the well-fed state when insulin is there? So in the well-fed state, when the hormones in insulin, so this enzyme is going to be dephosphorylated. On dephosphorylated, the kinase part is going to become active. So when there is insulin, dephosphorylation is going to take place, and in that case, on dephosphorylation, the kinase part becomes active and your bisphosphate part, it becomes inactive. This was in the case of insulin. So what happens? Your kinase is active. So phosphofructokinase, it is going to cause phosphorylation at position 2. So it forms fructose 2,6 bisphosphate. Okay, it is going to phosphorylize fructose 6-phosphate to form fructose 2,6 bisphosphate. Now what happens? This fructose 2,6 bisphosphate is going to activate phosphofructose kinase 1, which is a key enzyme in glycolysis. So your glycolysis is going to be active. So you see how under the influence of insulin, glycolysis is being activated. Now, what happens when there's no glycolysis? Okay, under the effect of glucagon, what is going to happen? Phosphorylation is going to take place. And when this tandem enzyme is phosphorylated, the kinase part becomes inactive and the phosphatase part, this becomes active. Now, when the phosphatase part is active, what will happen? It is going to remove phosphate from fructose 2,6 bisphosphate and form fructose 6 phosphate. So, as a result, what will happen? This activator for phosphofructose kinase 1, that is fructose 2,6 bisphosphate, is going to be active. Now, this phosphofructose kinase 1 is not going to be activated and your glycolysis will be decreased. So that is how reciprocal regulation is brought about by the two. Now talking about the significance, so it is significant in maintaining the blood glucose level during starvation. Okay, so in case of starvation, that is when this comes into role, your gluconeogenesis, to maintain the blood glucose level. And the substrate for gluconeogenesis, they are lactate, glucogenic amino acid. The principal glucogenic amino acid is your alanine, then glycerol and propionyl CoA. So these are the substrate for gluconeogenesis. So we've taken glycolysis, we're done with gluconeogenesis. Now another very important topic, that is glycogenesis, that is synthesis of glycogen. So we're going to begin with this now. So firstly, what is glycogen? Before I start with the cycle, so glycogen is the storage form of your carbohydrates. Okay, so glycogen is the storage form of carbohydrate. Now the question arises that why is glucose stored as glycogen? It could glucose can be stored as glucose. No, it is not stored as glucose because first of all, your glycogen is a highly branched polymer. Okay, so secondly, your glucose, it is able to absorb water. So on absorbing water, the cell will swell up. So these are two reasons why glucose is not stored as glucose, but rather it is converted to glycogen and then stored. So your glycogen is nothing but the storage form of carbohydrate. That is how you are storing glucose in your body. So the glucose in your body is stored as glycogen. Now this glycogen, it is a highly branched polymer, branched chain, homopolysaccharide, that is, it is made up of only one monomer and it is made up of exclusively alpha D glucose. Okay, so your glycogen is made up of alpha D glucose. Now what happens? It has a straight chain. So the straight chain has alpha 1,4 linkages and at branch point it has alpha 1,6 linkages. So if I like grammatically try to explain you, you can assume this to be your glycogen. So you see, this is a highly branched polymer and these branch points here, these are alpha 1,4 linkages, and in the straight chain here, you have all these alpha 1,4 linkages. Okay. Now let's talk about, and also what are the major sites of storage? They are your liver and muscles. Okay. So your glycogen is either stored in the liver, which is known as liver glycogen, or either stored in the muscle, known as muscle glycogen. Well, let's begin with the cycle. That is the steps in glycogen synthesis. So the synthesis, it has two steps. Firstly, you need to synthesize UDP glucose, because this UDP glucose is actually contributing the glycosyl residue needed for your glycogen synthesis. Okay. Then the reaction of glycogen synthase. So this is the rate limiting enzyme in glycogen synthesis, and then the branching. So let's see how your UDP glucose is first synthesized. Okay. So the alpha D glucose attached to uridine diphosphate is the source of all the glycosyl residue that are added to the growing polypeptide, growing glycogen molecule. That is, see, your UDP glucose, how are you forming your UDP glucose? Firstly, if you see, you have uridine triphosphate, okay? This is somewhat a rough structure of UTP, okay? Now, what is happening? You are going to add a glucose here and you end up with UDP glucose, okay? So you're going to remove this phosphate and instead add a glucose here. Okay, so that is what is happening, and this structure that you're ending with, which is known as UDP glucose, this UDP glucose is going to give glucose to the growing glycogen molecule. Okay, so that is how you're adding glucose to the glycogen molecule, and glucose as such, like direct glucose, is not being added. So first you need to synthesize UDP glucose, and how is UDP glucose being synthesized? It is being synthesized from UTP. So you need one UTP and you need what? Phosphate, okay, from glucose 1 phosphate, and then you're going to form UDP glucose. So what is happening? Your glucose first, it is going to be acted upon by hexokinase, and then this hexokinase, it is going to form glucose 6 phosphate. Now this glucose 6 phosphate, it changes into glucose 1 phosphate. This is brought about by a mutase enzyme. Okay. Now this glucose 1 phosphate is going to combine with UTP here, as you can see. So it is going to combine with UTP to form UDP. So this is how your UDP is being formed. So on the substrate side, you can see there was 1 phosphate and 3 phosphates in the UTP. So you had 4 phosphates. Okay. And you here you have what? UDP. So only 2 phosphates are there. So one pyrophosphate molecule is also released. So your UDP glucose has been synthesized. Now the next step is the reaction of glycogen synthase. Now what is happening? Your glycogen synthase is able to synthesize glycogen only on a primer. Okay, so glycogen synthase, it needs a primer to work. Glycogen synthase is also needing a primer. Now this primer, it can either be leftover fragments of glycogen or it is known as glycogenin. Now, what is glycogenin? Glycogenin, it is a it is a homodimeric protein having two identical monomers. Okay, so this glycogenin is nothing but it is a homodimeric protein. Okay, it has two identical monomers, and both these monomers, they are going to autoglycosylate each other and form a small oligonucleotide, that oligo uh, saccharide, okay, or approximately 7 unit longs. Okay, so it is going to auto glycosylate each other and add, make a small chain of almost 7 glucose residues. Okay, and this small chain of 7 glucose residues, this is going to act as a glycogenin primer. And now on this primer, what is going to happen? Your UDP glucose is going to come and give glucose. The enzyme is glycogen synthase, and you are going to form glycogen. So this is your primer. I'm showing it in green. On this primer, what is now going to happen? Your glycogen is going to be added like this. And this is brought about by the action of glycogen synthase. Now this is going to take place up to 7 residues. Okay. That is 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So after 11 residues, what is going to happen? Your branching enzyme is going to come. It is going to transfer this block here and it is going to create a branch. So this is the action of your branching enzyme. Now this is going to be more clear if you see this diagram. Here in this diagram, you can see your glycogenin. This primer is shown. On this primer, your glycogen synthase is acting. Your UDP glucose is coming and it is giving glucose. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So up till 9 to 11 residues long, it is going to add glucose. Then a block branching enzyme is going to come and transfers 6 glucose residues and forms a new branch point. So you see from here, these 6 glucose residues, they are transferred here and a branch point has been introduced by the branching point. And this is going to happen repeatedly. Again, glycogen synthase will add glucose residues. Again, branching point will transfer this here somewhere. And ultimately, you're going to end up with glycogen, which is going to look like this. Okay. So that was about glycogen synthesis. Your glycogen has been synthesized. The site is liver and muscle. Your organelle is cytoplasm, and glycogen synthesis is going to take place in the well-fed state. Obviously, under the effect of insulin, because you have so much of glucose, more than the energy you require. Now, this excess glucose that is going to be stored as glycogen. So, obviously, it is going to take place in the well-fed state. Now, talking about glycogenolysis. When is glycogenolysis going to take place? It was going to take place in the early fasting, like I told you. So, that is after you've had your meals from 4 to 16 hours. That is early fasting. Early fasting, your glycogen is going to be broken down to provide glucose. It takes place in the liver and the muscle. Let's talk about the steps involved in glycogenolysis. So the first step is action of glycogen phosphorylase. So this is the rate limiting enzyme, your glycogen phosphorylase. Your glycogen phosphorylase is going to act on glycogen and remove glucose as glucose 1-phosphate. Now that is important that your glycogen phosphorylase, it is going to remove glucose as glucose 1-phosphate, removes glucose as glucose 1-phosphate and not as glucose. Okay. So you end up after the action of glycogen phosphorylase, you're going to end up with a highly branched molecule which is known as limit dextrin. Okay, now what happens? You are going to remove branches. Okay, now the branches are going to be removed, and ultimately, what is going to happen? Your glucose 1-phosphate is going to be converted into glucose because the body needs glucose. It does not need glucose 1-phosphate. So that is the last step, conversion of glucose 1-phosphate into glucose. And now through this diagram, I'm going to explain you. See, this is your glycogen. At the branch point, you have alpha 1,4 linkages, alpha 1,6, sorry, that is at the branches, and the straight chain has alpha 1,4 linkages. Now, what is going to happen? Your glycogen phosphorylase is going to work on this glycogen molecule, and it is going to sequentially, that is one after the other, it is going to sequentially remove your glucose as glucose 1-phosphate. Okay, so you can see glucose 1-phosphate units, they are sequentially released. Glucose molecules as glucose 1-phosphate, they have been removed. Now what happens? Action of glycogen phosphorylase stops near the branching point. So 4 units away from the branching point, as you can see here, 1, 2, 3, 4. Your glycogen phosphorylase is cutting your glucose 1-phosphate and it stopped working 4 units away from the branch point. This was the branch point, so your glycogen phosphorylase stopped working here. Now what is going to happen? Debranching enzyme is going to come. Debranching enzyme is a tandem enzyme. It has 2 enzyme activities. One is transferase and one is your glucosidase activity. So this transferase, it is going to transfer this saccharide unit from here to this point, okay, the non-reducing end. So a trisaccharide unit, as you can see here, has here. You can see it has been transferred from here to here. Now what happens is going to remove this branching point, and now this that is removed from the glucosidase activity of the debranching enzyme, this is going to be removed as glucose. This is removed as glucose, okay? Now what happens? Again, your glycogen phosphorylase is going to work and it is going to remove glucose 1-phosphate units. So majorly what is happening in glycogenolysis, you are getting glucose 1-phosphate, okay, because most of the time glycogen phosphorylase is working Glycogen phosphorylase is working most of the time and it is giving you glucose 1 phosphate and alpha 1,6 glucosidase. This enzyme, it is only working at the branch point. So you're getting glucose only from the branch points and majorly you are getting what? You're getting glucose 1 phosphate. So therefore now you need to convert this glucose 1 phosphate to glucose. So in the liver, what is happening? There is enzyme known as glucose 6 phosphatase. Okay, so glucose 6 phosphatase, this glucose 1 phosphate is acted upon by an enzyme known as glucose. Firstly, your glucose 1 phosphate, it is going to be acted upon by an enzyme known as mutase and it is going to change into glucose 6 phosphate. Now, this glucose 6 phosphate is acted by an enzyme known as glucose 6 phosphatase. Phosphatases, as we know, they remove phosphate. So, it is going to remove phosphate and you end up with glucose. Okay. So, that is how your glucose is being formed from glucose 6 phosphatase. Now, in the muscle, what is happening? This enzyme, glucose 6 phosphatase, glucose 6 phosphatase enzyme, this is absent. So now what happens? The fate of glucose 6 phosphate. So in the muscles, what is going to happen? Your glucose 6 phosphate, it is going to enter anaerobic glycolysis. Anaerobic glycolysis. And it is going to provide ATP in case of muscle contraction or exercise. So as I told you, the two main storage organs for glycogen are liver and muscle. So your liver glycogen, it is involved in maintaining blood glucose level. It provides glucose. Okay, so it is involved in maintaining blood glucose level. And whereas your muscle glycogen, it is involved in providing energy during exercise. So both of them have different functions. So that was all that you needed to know about glycogenolysis. So the site is liver and muscle. Organelles is cytoplasm majorly, but 1 to 2% of it is also taking place in lysosome and smooth endoplasmic reticulum and takes place under the effect of glucagon, that is in the early fasting state, and energetics. One glucose residue derived from glycogen gives 3 ATPs. Why? Because the first step, that is the energy that was utilized by hexokinase, that is not taking place because it is already entering at the level of glucose 6 phosphate here, as you can see. So therefore, 3 ATPs you're getting in this case. Now talking about regulation of glycogen metabolism, that is both glycogen synthesis and glycogen breakdown. This is also very important, the regulation. So your glycogenolysis is occurring in fasting state. That is, breakdown of glycogen is taking place in the fasting state. That is when you need glucose. The blood glucose level is low. And glycogen synthesis is taking place in the well-fed state. That is when there is excess of glucose in the body. So you're going to store it as glycogen. Now, that was about the liver. Talking about the muscle, so your glycogen in the muscle will break down in case of exercise. So the body is exercising and for muscle contraction, you need ATP. So that ATP is going to be provided by the muscle glycogen. So in case of active exercise, that is when your glycogenolysis is taking place in the muscle and glycogen synthesis begin as soon as the muscle is at rest again. Now talking about the types of regulation, there's hormonal regulation and allosteric regulation. So we'll take the hormonal regulation first. As you can see here in the diagram, what is happening to glucagon or epinephrine is going to bind to its receptor and this activates what? Adenylyl cyclase. So adenylyl cyclase is activated and this adenylyl cyclase is going to change ATP into cyclic AMP. Now this cyclic AMP, it is going to activate inactive cyclic AMP dependent protein kinase A. So now you can see cyclic protein kinase A has been activated. Now this protein kinase A, it is going to activate glycogen phosphorylase A, kinase A. Now, this glycogen phosphorylase kinase A, it is going to activate the rate limiting enzyme, that is glycogen phosphorylase. So, on phosphorylation, your glycogen phosphorylase has been activated. So, this glycogen phosphorylase, it will break down the glycogen, and what will happen? Glycogenolysis is going to take place. So, that was about glycogenolysis under the effect of glucagon or epinephrine. Now, under the effect of glucagon or epinephrine, what is going to happen, or how is your glycogen synthesis being regulated? Let's see. So, same way, your glucagon is going to bind to its receptor. Adenylyl cyclase is going to increase the level of cyclic AMP. Now, this cyclic AMP, it is going to activate protein kinase A. Now, protein kinase A is active, so it is going to phosphorylate your glycogen synthase. But what happens when glycogen synthase is activated, it's phosphorylated, it becomes inactive. So on phosphorylation, your glycogen synthase is going to become inactive. Your glycogen phosphorylase, on phosphorylation, it was becoming active. But here, it's the opposite. So your glycogen synthase is becoming inactive on phosphorylation. Now what happens? Your glycogen synthesis is inhibited. So the synthesis of glycogen is inhibited under the effect of glucagon, and your glycogen phosphorylase is activated under the effect of glucagon. Therefore, degradation is activated. Now, what is insulin doing? Insulin, it favors protein phosphatases. So going to be favored, and phosphatases are enzyme that removes phosphate. So they're going to remove this phosphate from glycogen synthase, as a result of which your glycogen synthase is going to become dephosphorylated. And on dephosphorylation, what is going to happen? Your glycogen synthase is going to be active. So under the effect of insulin, your glycogen synthase is going to be active, and your glycogen is going to be synthesized. Now, similarly, what is happening when your insulin is going to activate phosphatase, and this phosphatase is going to dephosphorylate your glycogen phosphorylase. So, glycogen phosphorylase on dephosphorylation, it becomes inactive. Now, glycogen phosphorylase, it is inactive, then it will not be able to degrade glycogen, or we can say that glycogenolysis is inhibited. Okay, so that was under the effect of insulin. So that is how your hormonal regulation takes place. Now there is another chart to summarize the two diagrams that I've taken up separately. So you can see here, it says glucagon binds to its receptor in the liver, and epinephrine has receptor bound in the liver and the muscle. Then what happens? Cyclic AMP mediated activation of protein kinase A is going to take place. So your protein kinase A is activated by cyclic AMP. Now this protein kinase A, it is going to phosphorylate glycogen synthase, and your glycogen synthase won't be phosphorylated, it becomes inactive, and what is going to happen? Your glycogen synthesis is going to decrease. But on the other hand, when your phosphorylase kinase is phosphorylated, it becomes active, and what is going to happen? Your glycogenolysis is going to increase. That is, your breakdown of glycogen is going to increase. This was under the effect of glucagon. And also glucagon is activating on phosphorylation your inhibitors of phosphatase. Okay, so your phosphate inhibitors are activated. So what will happen? They're going to inhibit phosphatase, and this is going to help in the maintenance of phosphorylation. That is, your phosphatases are going to be inhibited, so they will not be removing phosphate anymore, and therefore your phosphorylation will be maintained. So that was a summary. This is again the summary. I don't need to take this up again. We're talking about allosteric regulation. So allosteric regulation is brought about in the liver and in the muscle. Let's see how. So there is instantaneous overriding of these hormonal controls by allosteric regulation. So your glycogenesis, that is glycogen synthesis, is stimulated when there is substrate availability and high energy levels. So obviously your glycogen synthesis is going to be activated when energy level is high. Okay, when there's a lot of glucose, lot of energy, then only you will be storing it. Okay, and substrate availability. And your glycogenolysis is stimulated when glucose and energy levels are low, just the opposite. So this is the diagram that is showing this. So in the liver, what is happening? From your glucose, your glycogen is being formed. That is your glycogen synthase. It is being activated by glucose 6 phosphatase, and vice versa. Your breakdown from glycogen to glucose, this glucose 6 phosphatase, it is going to inhibit your glycogen phosphorylase ATP, that is high energy. It is also going to inhibit glycogen phosphorylase, and it is going to activate your glycogen synthase. Similarly, glucose is also going to inhibit glycogen phosphorylase and activate your glycogen synthase. Same goes for the muscle. Now, apart from that, there's also activation of glycogenolysis by calcium. Okay, so we've already discussed hormonal regulation and the allosteric regulation, but apart from that, your glycogenolysis, that is your glycogen phosphorylase, it can also be activated by calcium. Now, this calcium can be released in response to contraction, that is in the muscle. It is released in response to exercise, and in the liver it is released in response to your epinephrine, okay, in case of fight or fear. So what is going to happen? This calcium is going to bind to a protein known as calmodulin, CAM. Now it is going to form a calmodulin calcium complex, and this complex, it is going to activate enzymes, okay. It is going to activate your phosphorylase kinase, and this phosphorylase kinase, it is going to activate glycogen phosphorylase kinase. So that is how your glycogenolysis will be activated. Now another thing is activation of glycogenolysis in phosphorylase is a little different isomer. So it is also having one binding site for AMP. So in case of extreme ATP depletion or anoxia, what is going to happen? AMP is going to bind to glycogen phosphorylase, and it is going to activate this muscle glycogen phosphorylase and bring about glycogenolysis. So we've discussed the regulation of glycogenolysis as well. So I think we've covered a major chunk. So we're done with glycolysis, we're done with gluconeogenesis, glycogenolysis, its regulation. So only TC and HMP in the important cycles were left. So we'll try to take time, or we can plan another Viva session on next Sunday. So I think a lot of your carbohydrate metabolism has been covered, especially the important cycles. This report and queries, this is nothing. If you open the textbook, you will see it's like almost less than half a page. So sometimes in short notes, you might get asked, so you should know. And fructose, galactose, and lactose metabolism, it's not that important. Only the clinical is important. Okay, so I think we've covered revised a major chunk of carbohydrate metabolism. I hope the class was useful. So quickly, I wanted to give you a flashback of the entire unit as much as was possible in this limited time span of 1 hour. Okay, so if you have any queries, you can send them. I hope the class was helpful. Okay, okay, hoping to see you in the next class. Take care.